I'm Altaf Hussain, former professor, Department of Chemistry, and the lecture series of A-level chemistry. This is the 26th lecture series, and I'll be talking about inorganic chemistry in this organic chemistry in this lecture. The next slide is I'm showing some pictures here. The first picture in the left, you see the man here, the clothes here, and the plate here, and the food here are all organic materials. If we go to next one, this slide, you see that skydivers, they can use their hand, leg to form chain, ring, like carbon atoms. If we go here, so we see that protein in muscles and enzymes to the DNA, which are our characteristics. These are organic materials. Come to this picture, the fuel, which is alkanes, usual fuels. The alkane, we do know about complete combustion and also incomplete combustion. The complete combustion gives us alkane plus oxygen, pure oxygen, and carbon dioxide and water. But incomplete conversion, octane, oxygen, air, and this gives us carbon monoxide and water. So incomplete combustion is a problem to our atmospheric problem, pollution problem. With all we deal will be organic chemistry. Next slide, if I go and say that there are 10 millions of chemical compounds, carbon-containing compounds. These are very, very, very much a huge number of compounds, you see, and these are increasing every day. Carbon is an amazing element. Carbon has alone far more number of compounds than all other elements put together. Most compounds contain organic compounds containing carbon and hydrogen. The main source of these compounds are living or once living materials in elements and plants. Because of this, the term organic chemistry is used to describe the branch of chemistry we study which containing carbon and hydrogen bonds. And please note that it is not only carbon and hydrogen bonds. There are also other bonding, for example, carbon dioxide, let's say, carbonate. And these carbon dioxide and carbonates do not have carbon-hydrogen bonding, but they are included in the study of inorganic chemistry. So, okay, the two main reasons for having so many compounds, carbon compounds, the first one is carbon atoms have an exceptional ability to form chain, branch chain, ring of varying size. No other element can have such a number of chains. The second reason that carbon can form so many compounds is the relative inertness and unreactive nature of carbon-carbon bond and carbon-hydrogen bond. When carbon atoms form a chain or ring linked by a single covalent bond, we see there not more than 2 bonds on each carbon atom are used. And that leaves at least 2 other bonds on each carbon atom which can be bonded with other atoms. So carbon often form bonds with hydrogen, oxygen, nitrogen, and halogen. Here we have an example, you see. This is what is carbon, atom. This is a carbon atom bonded with carbon-carbon, and then we have bond with hydrogen atoms. This is what white balls are: hydrogen atoms, hydrogen atoms, hydrogen atom, hydrogen atom, and then we have an oxygen atom here with bonded with hydrogen atom. So we have hydroxyl group in this organic compound. Well, there is a wide range of compounds, synthetic compounds, that is fuels, plastics, medicine, anesthetics, and antibiotics. If we do have good knowledge of organic chemistry, we can extract this, synthesize it, characterize this, etc. Sorry. Big molecules, the molecules in living things are mostly molecules of carbon atoms. So biochemistry and molecular biology are important application of organic chemistry. So here we are seeing a short section of a polythene molecule, a big number of molecules, and we see the molecules of these compounds are large, very, very large, a molecular mass of about 1 million or so. Organic chemists can synthesize other long chain molecules by linking together small molecules. The synthetic polymers include polythene and polystyrene, nylon, etc. Chemists have been, as I said, that 10 millions of compounds. So if we want to study this, we have to be a bit systematic and see how systematically we can study this. So we will deal with functional group of chemistry, and then see families of hydrocarbons, which sometimes called homologous series. So a family of similar compounds with same functional group is homologous series and can be represented by general formula. So we can take example alkanes, whose general formula is CN H2N plus 2. Alkenes, general formula is CN H2N. And we have also halogen alkanes containing one halogen atom. So general formula is CN H2N plus 1X. So we are talking about functional groups. So ethane, we have, this is the molecular formula. Ethanol, this is the molecular formula. This is what is displayed formula we call of ethane and ethanol. You see, it look almost similar, but then you see with the use of functional group, they differ. The properties differ very much. Ethane is gas, whereas ethanol is a liquid. Ethane does not react with phosphorus pentachloride, but ethanol reacts vigorously with phosphorus pentachloride, giving hydrogen chloride gas. So clearly the OH group in ethanol has a big effect on its properties. The OH group in ethanol, called hydroxyl group, is an example of functional group. So here we can take this example and see what is OH group and what are the bonds we have, etc. It's a ethanol, C2 and H, 1, 2, 3, 4, 5, 6, 6 and on O. So here is the, this is the functional group. This is what we call active functional group. These bonds are, this bond are relatively unreactive. I would say not relatively unreactive. These bonds are reactive. These bonds are reactive. So that is how we use the functional group and could characterize the or name the organic compounds. So this makes, okay, I've already talked about it. Let us say about this molecule. So the same functional group can be regarded as a chemical family-like group of elements, what we talked about in the periodic table. Ethanol is a member of the series of compounds called alcohols, all of which contain the OH group, functional groups. Ethene, the functional group is C double bond C. Okay, then we have to talk a little bit about the homologous series and functional group. And you see in the right, this table shows the number of functional groups and the name of the compounds, and also structural formula. So these functional groups are in the syllabus of AS level chemistry. So in our next few lectures, we will talk about these functional groups and their compounds, and see the reactions, what is happening with what are the different types of reaction we get. This will be discussed in next lectures. But some organic molecules can not only have one functional group, could be two or more functional groups. An example is lactic acid. You see, here what are the functional group? One functional group is hydroxyl group, we call alcohol functional group, and another, this one is this one. It's another functional group, it's carboxylic acid group, and this compound is known as lactic acid, or the chemical name we can call 2-hydroxypropanoic acid. 2-hydroxypropanoic acid. 2-hydroxypropanoic acid. This is the functional group. And we will see that this compound sometimes acts as acid and sometimes also acts as alcohol. So both properties are in this compound. Well, we have been discussing empirical formula, molecular formula, structural formula in our initial lectures. So if we remember, the empirical formula is a compound of a formula found by experiment. What we call about molecular formula, a compound shows the actual number of atoms of each element in one molecule. So this is a molecular formula. The ethanol has the molecular formula of ethanol, there's molecular formula of ammonia. Structural formula of a compound gives the number of atoms of each element in one molecule, but it does not show how the atoms are arranged. So to understand the properties of compounds, you need the structural formula. This shows which atom are bonded with which atoms, this etc. For example, here we will see that how this carbon atom is bonded with this carbon atoms, and this carbon atom is bonded with 3 hydrogen atoms and 2 hydrogen and functional group. So, and then often we call a displayed formula and skeletal formula also. A clear understanding of full structural formula we call displayed formula. This is the displayed formula of propane. Okay, and this is what is skeletal formula, where we only show the carbon bonds, nothing else, and functional group. Carbon bonds and functional group. Here you see, this is the molecular formula C3H8, and this is the structural formula. We show the 3 carbon atom and how the hydrogen atom are bonded, and this is the displayed formula. Here are 3 carbon atoms bonded with hydrogen atoms, and then skeletal formula. As we said, skeletal formula means only the bonding in carbon atom. That is, these 3 carbon atoms are shown 1, 2, 3. And now if we got this ethanol, what we see that here this is the structural displayed formula, this is structural formula, this is molecular formula, and the skeletal formula, we have 2 carbon atoms. This is the 2, 1, 2, and then functional group. 1, 2 carbon atom and then functional group. This is how we show the skeletal formula. Well, we said in the beginning that there are homologous series, and we also said the alkane is homologous series of hydrocarbon, and the general formula is this. So if we take the first four members of alkane, that is we call methane, ethane, propane, and butane. This is the first four compound of homologous series of alkanes. What we are doing here, we showed the most of the empirical formula, molecular formula, structural and displayed formula in this table. So you see here is the empirical formula of methane. We didn't write empirical formula of ethane here. There are some gap, and it is expected that the listener or the students will fill this gap and complete this table. So we showed here empirical formula, molecular formula. We didn't show the structural formula, but we showed the displayed formula. Similarly for ethane, we do have a gap here and do have a gap here, and we are expected to fill these gaps. Or for propane, for butane, similarly. And here you see a displayed formula of a hydrocarbon. We are expected to name this one. And how could we name it? That we just count the number of carbon atom: 1, 2, 3, 4, 5, 6. So this must be hexane. And when we talk about hexane, this is the displayed formula. What will be the skeletal formula? So you see, you have a skeletal formula: 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, and 6 carbon. So this is the skeletal formula of hexane. Well, this is a chain, but ring, hexane. This is one, it's also hexane, ring of hexane. This is not long chain, this is cycle ring chain. So here is 1, 2, 3, 4, 5, 6. So we could call it displayed formula, and this is the skeletal formula of hexane, ring hexane. Well, now we are talking a little bit about crude oil. What is crude oil? Which we often hear. The majority compounds found in a mixture of hydrocarbons which are known as alkanes. This is called crude oil. So this is in the left. Hydrocarbons was displayed, structural and skeletal formula are given. What is the name of this compound? What we do, immediately count the carbon atom: 1, 2, 3, 4, 5, and therefore it must be a pentane. The molecular formula of pentane is C5H12. Okay, and if you go here, you can see that this is also the skeletal formula of pentane: 1, 2, 3, 4, 5. Skeletal formula. So displayed formula, structured formula, skeletal formula, we can immediately write down of if a compound name is given or if a formula is given. Here we see the formula of displayed for three-dimensional structural formula of a pentane. Okay. This is what is carbon atom, and this is what is hydrogen atom, and it shows the three-dimensional. Why we are talking about it. So you see that three-dimensional formula of pentane, all the carbon-carbon bonds are single bond. When we talked about bonding, we showed in such case the carbon atom shows a sp3 hybridized bond, or carbon atom having an sp3 hybridization, and all the other bonds are filled with hydrogen atoms, and therefore this is called saturated hydrocarbons. That is, all atoms, all bonds of hydrogen carbon are filled, and that's why it is a saturated hydrocarbon. Well, it is very important to name these compounds systematically. And IUPAC, that is International Union of Pure and Applied Chemistry, they are the authority for naming chemical compounds. So, and they set some rules, and using those rules, we name chemical compounds, which we should do for inorganic compounds, organic compounds, and other compounds too, chemical compounds. So, how we name these compounds? Say, naming alkanes. We could name alkanes. You see that here it's only the first 10 hydrocarbon or alkane hydrocarbons are mentioned here in this table. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. It's very simple. We can do this. And what are the things we have to look for the hydrocarbon naming? The first thing that we have to look to the chain number carbon chain, and then we also have to look for branched chain too, and also see what are the radical or attached to it. For example, methyl radical or ethyl radical. So here we have alkyl group, which you call methyl, ethyl, propyl, butyl. If we from methane, if we take away one hydrogen atoms, and it becomes methyl group. From ethane, if we take a hydrogen group, then it's ethyl group. For propane, if we take hydrogen group, then it's the propyl group, butyl group, etc. So identifying the alkyl groups and attach the longest unbranched chain. So first identify this, that how many carbon atoms we have and unbranched chain carbon atom we have. For here you see we have 1, 2, 3, 4, 5 carbon atoms. So because it is a homologous series of alkanes, so it is pentane, and this one we have 1, 2, 3, 4, 5, 6, 7, and therefore it is heptane. Now the next question is we could have some alkyl group coming and having a branched chain too. So we have to consider that also and name accordingly. So that what we do, we have to number out the carbon first and see in which way it is branching. And the branched carbon branching, alkyl group branched here. For example, alkyl group branched here too. So we have to count the number depending on, you see here, we call it 2-methylpentane. A methyl alkyl group is branched in 2 positions. Well, you must have say now why it is 2 positions. Why not from there we count and find it 1, 2, 3, 4 is branched with 4. So why not 4-methylpentane? So answer is simply that we have to see the long chain and then see where is branched, and then we can count a number of carbon atoms from both ends, from this from the left end to and from the right end, depending on where it is branched. If it is branched close to the right end, we count from here. If it is branched, say let's say here, branching here, so we count from here. So this one we have to call it 2-methylpentane, not 4-methylpentane, because it has branched from the right in the second position. So similarly, if we go for here, we see where it is branched. So you see 1, 2, 3, 4 is branched here, but we see here 1, 2, 3 branched here. So from there, from here we have to count the carbon atoms. So why carbon atoms? 1, 2, 3, 4, 5, 6, 7. So it is a heptane. But the branching, if we go, so the branched first, it branched in the third position, third carbon atom, and second it's branched in the fourth carbon atom. So Then again we have to go alphabetically. So if we have a branching it to more than one, we go alphabetically then. So we have branched here and here is more than one. So we have to, this is a ethyl group and this is a methyl group. The alphabetically ethyl group comes first. So we call it 4-ethyl, 3-methyl heptane. And we cannot say 4-ethyl, 5-methyl pentane. You cannot count it from this branch because it is first branched here, smallest number here. So but we do like this branching, and then we have another 3-4 rules to be followed while counting and branching and naming the organic compounds as per IUPAC rules and regulation. We have two methyl groups are branched. So in this case we use, if two or more, then we use the prefix di, tri, tetra, etc. So here it is 2, so it's 2,3 dimethyl pentane. Not, we cannot say not 3,4 dimethyl pentane. We cannot say that. Similarly, we have talked about it, and in this way we count, see the name, carbon chain first, where it is branched, we have to then numbering the carbon atom similar accordingly, and then if it is more than 1 or 2, we use di, tri, tetra, etc., and name the compounds in alkanes compounds like this. Okay,